Thank you very much. It's a great honor to be here in KU Leuven. So one of my first events was Ches in, was that 2012? Yeah. So actually my first introduction to hardware security was right here. So it's really good to be back in this area. So what I'm going to talk about is what I call building better sledgehammers. So building better tools for embedded security. And there's a lot of demos in this talk. So if you have any questions, want to see stuff again, feel free to stop and let me know. Let me know if the audio needs adjusting or anything too, but otherwise I'll keep going. So about me, I started this project called Chip Whisper, which was basically, as Benedict mentioned, this sort of trying to solve this problem of building better tools. So when I started working on it, there's an opportunity to build more sort of open source accessible tooling, which turned into a pretty wide range of different tools. I'm going to be using some here. A lot of them are open source, so it's a combination of open source and less open source, but the idea is the core stuff for research is open. I'm going to be doing a lot of demos. You can go and look at all of the source code right now, look at the examples. So if this is something that interests you, it's something you can learn a lot more about right away. I'm currently with Dalhousie University, as well as an assistant professor in sort of the hardware security area, so a lot of side channel and fault injection. Alongside that, so a colleague from Riskier, a company that makes higher end commercial tools, as well, and I wrote a book about embedded security attacks, hardware hacking handbook together, which goes through some of these attacks. So if you're interested in this area as well, that's kind of a good resource. Okay, so what's this talk about? This talk is about what I call sledgehammers. Sledgehammers are a good example because it's not an offensive tool, right? So you could use it to break into a building, yes, but that's not the core purpose of it. So these tools are also designed not offensively. They could be used that way, but the point is to help people understand the security of their systems to make things better. So what I want to show you is how these sorts of tools could be used to attack embedded systems and what the attacks look like in practice. So it's teaching people how the attacks work. So there's a few sort of goals of this which tie into, when I originally started doing this work, what I thought was important. It's not just attack scripts. So there's lots of tools out there that say, hey, if you want to do this exact thing, this tool does it. And they're more offensive use because the goal is to exploit a system with a specific version of software. There's a script that runs the exploit, and that's all it does. You don't have to understand it. So I want to teach people how the attacks work. The other goal is to make accessible tools, so tools you can buy and use. So this is another big difference, right? The idea is that it's not just a tool that is only available to you at the university, but if you're doing this work on your own, a small company, it's also something you can use. So it's important to make sure that we're ensuring everyone has access to them. And doing this open source ties into 1 and 2, right? So if it's open source, you can understand how it works because you can look at the source code. If it's open source, it's probably more accessible because it's probably, the software is something you can access freely. You don't have to worry about export controls, about shipping things around. So as part of that, I mentioned here all the demos I'm running today are in this specific repository. So if you do want to see how they work, you can go look up that repo and almost all of this code is going to be here. Okay, so there's 2 things I'm going to talk about. Power analysis first and then fault injection. These are kind of the areas of this sort of straightforward physical attacks that we can do with low-cost equipment. The first one, power analysis, is a very simple way of understanding what a system is doing. Fundamentally, what we do is we have a microcontroller here. This microcontroller, we are monitoring the power going into it. We can monitor it a few different ways. What I'm using is a resistor so that as current is flowing across the resistor, there's a voltage which is the current times the resistance developed across it. This gives us a signal here that we measure. So you can measure this in an oscilloscope, or what I've done is I have some purpose-built hardware that's designed to more sensitively measure these variations. And we'll see a few different variations measured. The most basic is we can see what the device is doing, what sort of instructions and paths of code are being taken. More complex is we can actually see the data being processed. And how this works is that if we look at a data bus internally on the device, on every clock edge of this data bus, signals are being set high or low. And there's actually a relationship between how many of these lines get set high or low. And at a very small level, and I'll kind of show you what this looks like in a few minutes here, at a very small level, the signals being set high or low and the actual power consumption of the device. So you can actually get a lot more information out of this than you might expect at first glance. So as a first example here, what I'm going to do is run a password check. So let's see if this is working. Okay. So if I have a little embedded system here, just zoom in. Okay. So I have a little embedded system here that when it reboots, it's asking for a password. And so what I've done, by the way, in the front here, I have a little microcontroller that I'm programming with different source code examples. So attached to the microcontroller, I have a device that's measuring the power consumption. So this is how I'm going to get the waveforms that are coming up on the screen. But this is all kind of live. So zoom this out so you can see. Right, so if you put in a password, it'll say password fail. And we could use power analysis to try to understand what the actual password is. And what I'll do is I have a little thing here that is going to compare two different passwords. I'm going to compare one password which starts with an H and another password that starts with a 0. In this case, I know the correct password starts with an H. And so with power analysis, what we're going to do is zoom in. Come on. There we go. And there's two different power consumption traces here. One is in red, one is in blue. And so it's very hard to see the difference. You can probably just see a little bit of variations peeking out. So we see a blue one here, but they're otherwise overlain. And this is because the code is actually taking the same path so far. And there's some point in time where the code, if we go along, these two are going to start to vary drastically. So at this point in time, we can see the red and the blue are diverging. So through the power measurement, we actually know that the password starting with H and the password starting with 0 have taken different paths. And if I add one more into this, and so this is just using a Python library, and I could send like a complete password, right? So if I compare this with password, so now we're going to be comparing three things, H, 0, and password. And we kind of zoom in on that area where they started to diverge. Right, we can see that, again, there's one, the blue path is taking one path, and the other two are taking the same path. So if we do this with every possible initial character, what we would find is that there's only one character where it diverges. And so that's the starting point of our password. And so how we use this, oops, F12, for bypassing the whole password, right, is that we would just cycle through, because in this case, I know if I have the password like that, if we were brute forcing this, right, we have this problem of we need to do every possible password. If we had a very long password, this search space explodes. But with power analysis, what I'm doing is I'm searching that first character, right? So I would just say A, B, C, D, blah, blah, blah. Eventually, I'd figure out that first character is H. Once I know the first character is correct, I could then do the same brute force on the second character. So if I do this in my little demo here. So if I knew the first character was H, what I could do is compare the second character. So H1 versus, or H0 versus H1 versus HA. So I'm just comparing 3 second characters. Make this bigger. And again, what we'll see is that in this case, now the code space is going to diverge again at a later point in time because the first character has been successfully found. And it'll come down to finding the second character. So we basically just script this whole thing. So in this example, what this complete demo is doing is we don't just manually look at it and keep changing. We just build some code that actually scripts all the changes and would try every possibility for that first character to display the difference. So I won't run through the full thing because it takes a few minutes to run. But I'll just show you this first one doing a comparison of all, in this case, just all lowercase letters to spit out the password. So with a little bit of time, we could actually recover what the full password was. So this is just trying to overlay every possible guess for the first character and stuff like that. The interesting thing about this, so why the password attack is a good example, is that to do this attack, I needed to search down each character independent of the other one. So our search space wouldn't be the huge search space that explodes if this was a 10-character password. It would only be however many characters I was searching. You know, if this was 26, if it was just all lowercase letters, right, times however many characters it was. So the search space only grows linearly. So if it's 10 characters long, right, the search space is very reasonable. And I'm checking the system every time is how I'm able to maintain that small search space. We use the same sort of technique when we looked at cryptographically breaking algorithms as well. So I'll show you how we can break AES with a similar sort of attack. Okay, so back to the point of this thing, better Sledgehammer. So what I'm using here is this Chip Whisperer Husky, which is a later version of some of this initial tools I built. The original Chip Whisperer design used a FPGA board here. And this FPGA board had some analog digital converters kind of connected to it. And these are what's giving us our nice power traces here. So the same sort of stuff is in this later design. This later design also adds things like you can trace on ARM debug. So ARM ETM, there's this debug capture format, so you can actually figure out what your power trace is doing and correlate it with instructions being decoded. So it's really useful for developing algorithms and testing them. Okay, so what's a real example? You know, this was just me programming a microcontroller. You might say that doesn't seem very realistic. So a real example of this is from an automotive ECU. They have something called boot assist module. This boot assist module is a serial loader. So it's their kind of low-level bootloader that's always enabled on some versions. To protect it for security, they have a password. And so this password, you load in 1 byte at a time. So you load in 1 byte, and then if the password's correct, it's going to load your second stage bootloader, which lets you extract data from the device. So this is how they sort of protect their whole system. And this bootloader has a pretty easy way of finding the location of the password check. The final check isn't as easy to exploit with power analysis, but it's very easy to exploit the instruction differences to find what happens with the correct and incorrect signature. So we're actually going to use this timing information when we introduce fault injection attacks to show another way of bypassing this password. But whether you use power analysis to directly bypass the system or to understand what level of exploitability it has, it's a really useful tool for this type of work. Okay, so let's look at, or keep this for a second, another example. So this is moving from simple power analysis to differential power analysis. So now I'm actually going to be exploiting these small variations to figure out the number of data bits set to a specific state on the internal bus. And so if I have AES running, what I'm going to be doing is I'm actually going to program in this AES algorithm into my little microcontroller on the board here, and then I'm going to send data to the microcontroller. It's going to encrypt it, and it's going to send it back to me. It's going to run the AES algorithm, which is shown here. And so what I want to point out is that we're going to see this structure in our power traces. So we have some different unique steps. We have these rounds that are running, right? So we're also wanting to see that we have a bunch of encryption rounds running. So we have subbytes, shift rows, mixed columns, add round key, and that just repeats until the final round looks a little different. So we'll actually see this structure in our power trace. So it's interesting that we'll be able to see a combination of what the device is doing as well as the data being processed. Where's this one? Okay, so now I'm going to program in an AES example. So using the same microcontroller, I just program in different code here. Takes a second to program. And then we'll see if it'll show you the real-time plot. Otherwise, we can look at the data after. Okay, there we go. So in here, we actually have parts of the AES algorithm running. And let's zoom out a bit. Right now, it's just showing you a smaller amount of data. Oops. Plot length equals 5,000. Okay. So this is showing you part of AES as it's running. And you can sort of see this structure I talked about. So you can see a block here, a block here, a block here, a block here, and then this block here is sort of repeating. So the interesting thing is that let's just turn off zoom. This block right here, where my cursor is, right, looks very similar to this block here, because this is actually the AES state, or the AES rounds continuing. So we have 1, 2, 3, and this is in the middle here, 4. So you have these 4 unique sort of states. This is the AES round as it's continuing. So the full AES is off the screen. I've only recorded part of the power trace, because what we're actually going to be exploiting is we're going to be looking at the data right after the subbytes operation here. So we're going to be finding out, finding leakage here. So how this works is we're basically going to be taking the fact that we have this very simple model of, or knowledge of how AES works, which effectively means it's adding in a key to our input, and it puts it through the S box here. So at that point, if I put a dot here, there's a dot on the little diagram, a dot on the input to AES. And so we're going to figure out the Hamming weight here, which is basically just the number of ones, which is what I mentioned through side channel power analysis, we're able to determine. And so how we use this to actually attack the system is that because we know the number of ones at this point in time, we know our input data. What we don't know is this secret key. I'll draw in green here, right? So this is an unknown. But we use the fact we have this simple model of the system. We can basically guess what the key is because we can put in different keys until we see a correlation between the Hamming weight that we measure and the Hamming weight that our model would estimate, because we know this input as well. So because we know the lines in blue, or we can measure them, one we know, one we measure, we can guess the key in green until we see a match. And so that's what the attack's going to do. And it'll take a very short amount of time to do this. So the interesting thing is that, AES, if you were to brute force it, is sort of like a heat death of the universe timing. But if I run this little attack here, the correct key is known in red. So you can see it very quickly highlights the correct key. And there's a number below it, which is the correlation. And that number below it is kind of showing how well correlated my measurement is with the estimate of sort of what it expects the correct key to be. So there's a value here of 0.893, for example. So you can see they're all around 0.8 to 0.9. So this is a very high correlation. The next best guess, so what it's doing is it's correlating every possible guess. For each of these key bytes, there would be 256 values here. I've cut it off so this table is more visible. But you can see the next best guess is at like 0.3. So it's very distinct what the correct correlation is. So it's a very effective attack on algorithms which aren't well protected against this. So you can see it's, it works, I would say, shockingly well in many ways for an algorithm that's very secure, otherwise very good. The implementation I'm running is a standard implementation. It's not artificial or anything like that. It's one that is used by people. And so this kind of gives you an idea of what side channel power analysis or differential power analysis in particular can look like. Okay. The other thing I wanted to show is of these two measurements, the small amount of difference. So if I have, let's start here, constant input data. So what I've done is I've zoomed in on one little section of the power trace where I've kept the input data constant compared to where I've kept the input data changing. So it is a very small amounts of variation that you're seeing because there's a little bit of noise. But you can see here, let's see, there's a point at this point in time, for example, we zoom in, where it appears that there is, small differences in what the path is taking. So this is related to the different number of ones in the data bus. When the input data is constant, and it's gonna also look like there's some variation here, but this is a little bit more just sort of random noise that you're seeing than you are seeing the more distinct changes with the changing input data. But the big proof of this is that you do see this really quick correlation of the correct key with my measured data to show you that it's working. So yeah, so that's a little example of using differential power analysis or correlation power analysis for breaking AES, which is a pretty classic demo, but it's something that you can do, again, really easily with a lot of different systems. And I actually think, just pull up this other one just to show you where, you could do this on, and I'll check after if I have the photo, you can do this on an Arduino, you can do this against a lot of different targets. So you don't have to just use purpose-built hardware, you can do this with your own equipment, with an oscilloscope, things like that. But the important thing here is that, if the secret's handled, whether that's the password or whether that's the key, it's pretty likely that the value can be leaked with power analysis. So to bring it back to the point of this, that, if you're doing these attacks, what is it teaching you? It can teach you a few things. One of them is that you can work on special implementations that avoid this leakage, but you can also architect your system to make sure the value can't be leaked. So if you're using public keys, for example, if you don't need to use a shared key and you can get away with using a public key, that's much more secure because it doesn't matter if that's leaked, right? There's no security in the public key being leaked. So you do see devices on the embedded side that do not need to use symmetric crypto, but they use it anyway. And then when a secret key in symmetric crypto is leaked, that's very bad. If they had chosen to use asymmetric with a public key, the problem wouldn't have existed. The other thing is using unique keys per device. So if you had a unique key per device, you could at least kill that key or not trust that key anymore if you knew it was leaked. So there's lots of things like this that when you consider, if I know for sure that this attack could work really well, I'm going to design my system more securely to start with. Okay, so the second thing I wanted to talk about was fault injection on microcontrollers. So fault injection is another really powerful attack. Some people say more powerful. I don't know. It depends what you're trying to achieve. But fault injection is interesting because if we had this code here, so this was from sort of a bootloader type code, and I've modified it a bit to be more generic, but we have this function that is called when there's a new firmware image to boot. As one does for security, there's a signature check on the image. If that signature is good, it will boot the image. Otherwise, it goes into an infinite loop. So this infinite loop might be hidden away, but it might be, in like a kill function or something like that. But the point is, once the device realizes, oh no, I can't do anything, the signature is bad, I have to just wait. It might be waiting for a watchdog timeout, whatever it is, there's some point where it just starts to wait. So if we do fault injection, what we're doing is we're actually saying that we're able to modify the device to there's many things we could do. The easiest is to erase or skip an instruction. So if we could not call the signature check, if we had this function and we could change the function flow so it didn't do the signature check, you'd imagine it would go just into do boot. Fault injection can be pretty powerful because the truth is actually even trickier than that. If I take my C code and I just compile it, the compilation rearranges the code a little bit in a way that doesn't impact the functionality, but does impact how I'm able to do this, this attack. And so the reason is over here, this bootload function has that signature check. So that's what I talked about skipping. But the way the program flow is written, you'll notice that this infinite loop has been put up here, right? So this is just a normal ARM compiler often does this. Even though the code on the left, I've written it in one order, it switched it around because it doesn't matter. But what does matter for fault injection is how much easier, right, to bypass the signature check. I needed to bypass this exact one instant in time. I had to hit that exact instance, otherwise I'm, hitting something else that isn't what I want to do. I have to be cycle accurate, which actually isn't that difficult, but is more difficult than what the compilers let me do now, which is there's a while loop here. And if I hit this while loop at any point in time, it's going to jump out of it, right, and go into the rest of the code, which is then my other program flow. So because of the compiler's choices, we have a really, really easy system to do fault injection against. Which is, again, one of the points of making these tools accessible is that if you knew this is a risk, and you take your code and you look at the decompiled version of it, you would immediately see that this could be a problem. If you didn't know this could even be a problem, you might just happily go along until someone does fault injection on your code. So yeah, now we can really easily do an attack there. A similar thing happens with reading past the end of buffers. So to do this code, by the way, I wanted to show you, there's a really cool website, if you haven't used it, godbolt.org, called Compiler Explorer. So this is what I'm using to give me, as you write code on the left, it gives you the compiled code over here. And I forgot to connect to the internet, so I'm not going to change it live. But yeah, so if you write code on the left, it'll modify it. And so you can see stuff like, hey, is it putting that while loop where I expect it to be and things like that. As an example here, one interesting thing is that I have this while loop, and this while loop is going through, it's pretty common in C or embedded systems. You have a code like this. You say, while this loop starts at 0, while I is less than 5, because I want to print 5 characters long, go ahead and write this buffer to my serial port. Very straightforward. But the tiny change it did here is this comparison point, I is less than 5. So on the right, it's highlighted in red, compare register 4 with fixed value 5. This BNE, if you don't know ARM assembly, means branch of not equal. So what's kind of odd about that is I've told it I is less than. The compiler has said, well, it's equivalent to say, because I'm incrementing, let's just branch of not equal to 5. So let's keep that loop going until we see exactly 5. But from a fault injection perspective, this isn't great, because if I can, for one loop, make that value, skip that instruction, so now I is equal to 6, it never saw 5, it's just going to keep looping through, right? So because of this tiny change in the compiler has actually made fault injection a lot easier for an attacker to do. So that's kind of one of the interesting things. And let's just see if I think it won't work without the internet, but yeah, okay. So so you can adjust it lots and see it all connect afterwards. But yeah, so that's what's kind of interesting about all of these things, is that with a little bit of knowledge about how the system's working, it makes it a lot easier for you to understand these attacks. Okay, so that's what I just talked about, right? Because we had this I is less than 5, if we skip that once, we'll just loop through the entire loop, and then it's going to just print out our whole buffer. Okay, so where do these come from? Fundamentally, if you're doing embedded systems, you have these internal registers that are used all over the place. If you looked at a processor, right, even a very simple microcontroller has, it's getting what instruction it's going to execute. It's going to take that instruction, it's going to execute it, and it's going to write data to internal registers, states, and things like that. So you have all of these sequences. Between all of these sequences, we have a bunch of flip-flops like this. So we have flip-flops, and we have combinational logic, which is all the logic that implements these functions, implements the ALU, implements decoding, whatnot. Why we can glitch this so effectively is that we basically have this design where we have these flip-flops. The flip-flops get a clock, right? So a fundamental part of digital systems is we have this clock, right? Your desktop computer is running at gigahertz potentially. That's how fast this clock is running. That's how fast data is moving between registers. In between this clock network, this combinational logic is a little bit slower. So that's kind of what sets our maximum speed, because between each clock, data needs to get from here through this combinational logic to here. If it doesn't make it in time, the wrong data gets loaded. So what you can imagine is that if I'm executing instructions and the data doesn't make it in time for the clock, it's going to either execute the wrong instruction because it's got malformed, maybe the previous instruction. And so there's a few ways of doing fault injection. One way is that you actually could insert, we're supposed to have a nice clock signal like this, but we could insert weird clock signals. So a normal one and then like a short clock pulse there. So suddenly I have this very narrow clock, right? And data won't have time to actually reach the second stage of the flip-flop. So I've purposely introduced a very narrow clock pulse that's going to introduce incorrect data. It gets even a little worse than I described there, because there's this issue called metastability with flip-flops. So with metastability, what we have is that the internal construction of flip-flops actually has this sort of feedback method where we have basic NAND gates. The output feeds back into the other one. If they enter an invalid state, so internally, these should always be opposite, 1 and 0, or 0 and 1. If they enter an invalid state, it eventually has to kind of resolve to either 1 being 1 and 1 being 0, but there's sort of a time where they fight each other. So we call this a metastable state. It's not stable. It has to resolve to a stable state. This happens when the data can change too quickly. So if the data changes too quickly relative to a clock, it can also cause this. Because as you can see at the input, you know, if I have a data going to 1 here, this becomes a 1. It has to transfer through another gate in one leg. So this is why we have to be very careful with the timing, is that if the clock comes at the wrong time, it's not seeing the correctly complemented data, and it enters this metastable state. The fact it takes longer to resolve means that a corruption on one flip-flop can kind of propagate to additional parts in the system. And so you can actually test this. For example, this was a quick experiment I did where I purposely feed in data that's changing too close to the clock, and I measure what the output happens. So at the top here, this is what should happen. I have data in and data out. It's always 1 or 0. So it's always changing to be, and I'm just randomly changing it to 1 or 0. But you can see it's always following this nice clean path. When we enter metastable states here, we actually see that the data does not change. Even though the clock changed at the same time, the output data took a lot longer to resolve to a 1 or a 0. So it's not just the case that I clock invalid data in. I actually can get into these really weird timing states. You can kind of see, and it's easier to see here where I've raised the power. So as I lower the voltage, it increases how long this metastable state lasts. So if I raise the voltage again, you also see these yellow lines here, which weren't present in my valid one, are because the device is sometimes keeping the same state. So it should always be changing from 1 to 0. But when I've entered this metastable state, it sometimes goes from 1 to 1 or 0 to 0. Because, again, we're violating the timing. It's not guaranteed that it's going to give me the correct output. So there's sort of a few physical reasons that we see fault injection being so effective. And by effective, I mean we get it to corrupt data, we get it to skip instructions, and things like that. So this is what like the clock glitches look like if you were to measure them with a scope. So again, it's a regular clock here, and then I've inserted a very narrow clock at some point in time. Voltage glitches. So an easy way to insert voltage glitches I'm going to use here as a demo are we drop the power supply of the device. And the reason this works well is that as the voltage goes down, so this is the voltage, this is high, this is low, so it looks a bit backwards. But as the voltage goes down, the propagation delay goes up, which is the same thing I showed here. Lower voltage gave me longer propagation delay. But back to this, if I have a longer propagation delay, this means stuff doesn't move through my combinational logic as fast. So this is also, if I can just, for a very short period of time, I increase how long it takes data to move. And I do this just for a short period of time because what I do is I narrowly drop the voltage, right, for a few hundred nanoseconds like I do here. It's only in that instance in time is the processor suddenly experiencing this weird state where data is not moving. So suddenly I can choose where in time I'm introducing these sort of glitches. So on a Raspberry Pi, here's an example of voltage glitching. What I've done is I've soldered a wire right onto a power pin on the underside of it, and I connect a MOSFET, a digital switch, to short the power at a very short instance in time. So this works on a whole wide range of devices, and it's a really easy way of doing glitching. Another way of doing glitching is with electromagnetic fault injection. So I use this to round out the earlier discussion of that a bootloader in the automotive device. So with electromagnetic fault injection, what I have is I have a coil of wire. I insert a powerful voltage or a high voltage into this coil of wire, which gives me a high current. This high current gives me a strong magnetic field. The strong magnetic field induces a voltage underneath it in the target. So this example was on a Bitcoin wallet. So it used EMFI over a microcontroller in a Bitcoin wallet. But we can do this on a wide variety of devices. So another example was on an automotive ECU, which is here, which was also demoed on some sort of the same chip in different scenarios. And the point of this was I had that password location identified with power analysis. So I knew somewhere in here, the device is doing something with my password check. And rather than using power analysis, I wanted to use fault injection to bypass the password. So I want the device to go try and check what the password is, and at the last instance in time, take the incorrect code path. Take the code path as if my password was correct. And so this was from this work on automotive ECUs. To give you an idea, right, the success rate can vary widely. So in this case, I was having like a 1% success rate on most of the devices here. On one of the devices, it was suddenly super successful, like 36%. But so with fault injection, we're not guaranteed to always be successful. I mean, you're never guaranteed success, but with fault injection, we normally want to structure it such that if I'm successful once, I had access to the system to rewrite some password or something like that. So once fault injection worked once, I could then do a complete attack against the system and recover all the flash files. Okay, so that's enough of that. Let's look at it working. Okay, so the first thing I'll do is show you, where's my, so I'm gonna run a few different demos here. The first one I'm gonna do is with voltage glitching. So what I'm gonna do is I'm gonna just demo or actually, let's switch that. I'm gonna start with EMFI and then go back to fault injection.
While Colin's setting up, I circulate the second list. This is only for the students in the Panama. Those of you who are concerned with this know. Type your name, just sign next to your name. Otherwise, if it's not for you, just pass it on. Thanks.
Okay, so it'll just program. So what I'm going to do is I'm going to program in a small little test into this microcontroller. What this test is going to do, it's going to just run through a loop. So the loop is something that's extremely vulnerable to fault injection. So it makes it easy for us to see if we're getting any fault. So I'll show you with EMFI first, and then we'll move on to other methods. And I interrupted this by accident, so rerun it here. And so you'll notice too, if you look at this, it's I'm actually rebuilding the firmware file. So one of the ideas of the Chip Whisperer is it has a whole bunch of source code and documentation available. So you can look at the firmware if you want. You can rebuild it for different targets. I'm using a SAM4S, which is a little Cortex-M microcontroller. But you can run other, there's examples on AVRs and larger devices. So this probably doesn't look super interesting, but what it's doing is it's running through a loop 200 times, 200 times. Each time it's incrementing some variables, and then it's printing that 40,000. So if any faults happen in the microcontroller, it's going to cause either the device to reset, which you'll see the count return back to 0, or it'll cause the counts to be slightly wrong. So I have a small tool here that generates a small magnetic field. And if I put it over the chip and hit the button, you'll see that hello is the device rebooting. And if we just kind of move it around, we may or may not get this. What I want to see is a number that's slightly wrong. And so normally we'd have, and so Leonard Lab would have a nice table that scans over this. So maybe he'll demo it for you if you want. But if you just kind of freehand it, you may or may not get it successfully. So what we would normally do is have that. And so here you can see it just crashed fully. So if I hit the reset button, it comes back. So a better way of doing this, though, is to actually have some way to scan through it. So rather than just staying here forever, I'm going to switch to other fault injection modes that are easier to demo. Okay, so what I'm going to switch to is first voltage glitching attacks. So to do this, I'm just going to use my chip whisperer, which has that little crowbar set up. And I'm going to basically connect a line to the crowbar. So it'll take the power rail down on the device at a really specific instance in time. And so I'm going to kind of automate my cert. So what I have is I have some code. Just run through this. I have some code that is programmed with that same loop check. Except instead of me just staring at the loop check, it's going to automatically check the value and then plot in a little graph here if it's seen a normal value or a reset. And so we use this to figure out what parameters are interesting. And so as it's running through, we can see there's a thing here that's saying normal count. Normal means the device was unimpacted. Reset means the device reset. And success will mean that it actually saw a value that was corrupt. So there is a few different ways of, oops. Come on. There we go. There's a few different ways of looking at this. So we can look at voltage glitching. We can look at clock glitching. All of them are going to give us some interesting parameters that potentially are going to allow us to exploit a system. So what might we want to exploit? A few different examples here. One example would be just doing an attack against this password check or anything like this. Another example is actually doing differential fault analysis. So there's a kind of cool attack against RSA. With RSA, there's a common speed up to RSA that splits the P and Q up. And when you perform the RSA signature signing operation, rather than doing it, so what we would normally do this on is we do this on something called the N value, which would be P times Q, which is our the number that we would need to factor if we were to break this mathematically. So because these operations on these big numbers are so slow, a common speed up is to actually split this up into P and Q separately. So rather than doing an operation on this large N value, we do it individually on the P and Q. So if we corrupt one of these operations, we end up with a factorable value. So we no longer are using the original integers that were supposed to be selected. We're using some version of it that's corrupted. The result of this is that we get a really easy way to factor. So again, what should be an impossible heat death of the universe sort of factoring problem, even without quantum computers, becomes a really easy thing to do on my desktop. There's two ways to do it. So in the slides, I also mentioned there's two explanations for this. The one that I find easier is that we just look at the fact, well, there's P and Q. These should be unfactorable integers when we combine them, or difficult to factor. If we make one of them no longer prime, it becomes very easy to factor. There's a second way using binomial theorem that results in the same thing. If we corrupt one of these calculations as it's happening, then it becomes very factorable. So that's what I'm going to show you. So to get there, though, first what I would want to do is find some successful value. So here it's found success count 3. Let's just stop this. Okay. And so what you can see here is this is the kind of graph we'd get. The X's are resets. And if this ran for a while, what we'd want to see is there might be an area with a whole bunch of successful. So the green, there's some green hidden behind that red X. So some of these are successes, some of these are resets. Normally a glitch happens right on the, right on the kind of interface between normal and bad operations. So it's pretty common that we'd get successes around resets as well. But I'm actually going to do this. So that's with voltage fault injection. I'm going to do this with clock fault injection. So I could run the same sort of test with clock fault injection, and that would give me another span of, okay, here are relevant parameters for clock fault injection. It takes a minute, so I won't do that. So I'm kind of using some existing parameters that I know work well. So I can skip right to showing you a fault attack on RSA. And so I'm going to program this with RSA. So this is coming from embed TLS. So again, these are all real. So embed TLS uses this Chinese remainder theorem, this speed up solution that's very, very common in real implementations. And switch this around. And so what I'm going to do is first I'm going to show you, so this device is running RSA, the little microcontroller. I'm asking it to sign something, so the attack is applicable when I can ask the device to sign an operation. This is commonly used, right? So this signing operation would be used if this was like a smart card, and I was asking the smart card to verify itself, to verify it had access to a private key. This signing operation would be exactly what you'd be using. And I'm sending it a message, it signs the message and returns the signature back to me. RSA is relatively slow. There's no accelerator in here. So this is the clock cycles it's taking. So it's 13 million clock cycles to perform RSA. What's kind of cool about this attack is that RSA spends most of the time doing one operation and then the other. At a meta point, it's working on P and then on Q, and then there's a tiny bit of effort to combine the two, but most of the effort is in P and Q. So when I do the fault attack, I don't, again, need very high resolution at all. I just have to hit roughly one half or the other half, which is what it's doing almost all of the time. So I can just kind of guess with my fault injection attack, okay, I'm guessing, let's just set it to half and a little before half. So that's exactly what I do. Okay, so here, this is just sort of verifying the signature is working. But here, I'm basically saying, that was 13 million. I'm setting it around 7 million and a little over. And let's just sweep through. So let's just try to get a fault somewhere useful in that area. And so if we do that, the device is going to basically, hopefully, either, there we go. Okay, so it took about 2 tries. So one time it crashed, the next time it glitched. We don't know if this is a useful attack yet. What we'll do is we get back the faulty signature. If this works, the faulty signature is one where we can very quickly factor it. And if we can quickly factor it, hopefully it gives us one of the P or Q values, because what's happening is that we're going to be able to factor out one of these 2 values. We don't actually know necessarily which one. And then we can use the original value of n. If we know n, so n equals P times Q. Oops. So if we know n and we know P, for example, or Q, whichever, we can then immediately calculate the missing value. So the problem becomes extremely easy for us to do. We no longer have this complicated factoring problem that, again, would take a huge amount of time to do. We can do this almost instantaneously. Okay, so then all this is doing here, the try except is just, there's two different ways of doing it. There's a faster library that's figuring out the greatest common denominator between the end value, which is always known, that's not a secret, and our message, our incorrect signature. And almost right away there, it returns one of the values, either P or Q, we don't know which one. And then we just divide n by that value to get us the other value. So now we have what we think are the two P and Q values. The rest of the values can all be derived from that. We can figure out the rest of the values and effectively generate our own RSA private key that we've recovered from the device. And the final test is that we take a message and confirm that we can in fact generate that same signature. Or take a message and confirm the device would successfully accept our signature. Whichever way we do it, we basically prove that we're able to get this to work. So, and I can adjust if this is P or Q. One thing I can show you as well is that so here this C36D0, and here I had C00. So one of these is P, one of these is Q. In theory, if I switch around where I'm glitching, so let's change this to be earlier. And I don't know if I already was too early. We'll find out in a second. What I want to see is that if this gives me the other value, so C36, okay, so C00. So I switched from recovering P to recovering Q, or vice versa, Q to P. And then this calculated the other one. So you can see, depending which I glitch, it gives me either P or Q really quickly. But yeah, so that's, in a few seconds here, I'm basically able to break RSA, again, which should be, or is a very secure algorithm, just with some known attacks against it. And there's countermeasures to this. So the most common countermeasure is that basically in the RSA calculation, you can figure out if someone has glitched it and you're returning an invalid signature. This is a check that you can then glitch, so it can get a tiny bit more complicated as described here, but it's actually not a super complicated attack, because basically then we just glitch past this additional check. So when the normal RSA is implemented in embed TLS, it has some protection against this, but it's not really sufficient for an embedded system where someone might be attacking. Okay, so yeah, so that's kind of what I wanted to talk about. Why build better sledgehammers? The point of this is that these solutions, or building secure solutions, need you to understand the attacks, and it's sort of this intuitive feel, right? And I go back to this again repeatedly, because the point is that if you knew fault injection could be an issue, and you saw this implementation of your code, you wrote the code on the left, you saw this code, you would almost immediately say, okay, this is very bad. Even if I'm not trying to design a super secure system, knowing that this loop has been inserted in front of my sensitive code is not something I should be very happy with, because it's going to be very, very easy to perform fault injection. The point with this loop is that I could perform fault injection with my little handheld EMFI tool, because I don't need timing anymore. There's no timing requirement. The device is stuck in this loop for a while. It's stuck in that loop until it resets or I glitch it. So I might want to change my code flow so that it doesn't do that. I could go further and make this more fault injection resistant code, but even without caring a whole lot, I've realized that there could be an issue. And it's the same thing with power analysis, right? The point that if the secret's handled and you don't do anything special, it's almost guaranteed that the value is going to be leaked somewhere. So I could go to mass implementation. I could just try to re-architect my system so that the secret is more difficult to leak or isn't really available. Go back to the end. There we go. So yeah, so hopefully this has shown you, that you can do this pretty hands-on. There's a lot of information out there, so I've tried to make more open source information available. There's a lot of good resources, lots of good examples here at KU Leuven online, GitHub and things like that, as well as doing these types of attacks. But yeah, so thanks for listening, and I think there's some time for questions if you have or want to see more demos too. I have more demos I can run, but.
All right. Thanks very much. And we indeed do have some time for questions or comments or whatever. I know it's early morning, but it was an entertaining talk. Questions?
I was wondering with the AES, why did you specifically do some full injection or like look at the power after the S-box? Was that intentional or is it just like convenient?
So why, let me pull this back up here. Where was that? Okay, so why we use just that one spot. Yeah, so it is convenient. There's kind of two reasons for it. Let me actually pull up, let me just see if I have a better slide set that might have this answered. I can't remember if, okay, there we go. So yeah, so it is convenient. This is kind of like the basic setup for side channel power analysis is we have some secret, what we really need for this to be successful is we need some input data that somehow is sort of connected to the key or like used. So if you XOR the input and the secret key. So you could do the power analysis right here as well, just after the XOR. This works, and the problem is that it gives you more solutions than you want because you sort of have this this problem that there's a linear relationship between the input data and the secret key. We get a little better results, or we get better results if we do this after the S box here, because it has introduced this nonlinear element to us. So when we do the power consumption, if we just use the XOR operation, it will work, but we're going to have the problem that we can't tell the difference between the complement of it. So if we have the correct answer and the complement, it's going to look the same because both will have the same linear relationship. So if we do it after the S box, it eliminates that. We guarantee that we're going to get only the correct answer is going to give us the high correlation. We're not going to have these other linearly related ones. So yeah, it's a minor kind of technical reason they do it. If the device didn't have a S box, you can still do it with just the XOR. You can use this, for example, if you're looking at an AES and it was like in counter mode or something where you didn't have the same ability to look after the S box because the input data was fixed. So you can choose other points is the quick answer, but it's just kind of a convenience of that exact attack.
More questions? Here's your chance. No more questions? Okay, it was also, I think, quite accessible and lots of demos, so easy to follow and yeah, nice and entertaining. There's one, okay, go ahead.
One question. How do you know when the microcontroller has reset?
So
Program it in, or do you use power analysis for that as well?
So you can do both. So in this case, what I have is it just has a, see if I had the exact, okay, no. It has a signal it sends back when it resets, so you can detect it's resetting. In real life, you can just use power analysis. Most microcontrollers have some sort of obvious boot up, either over serial or in the case of the automotive one, it has a, let's see if I have that up here. Okay, no. I don't have the pinout stuff, but this automotive microcontroller has a reset out pin, and it actually asserts that reset when it goes into a reset state. So you can also use that. Not all have that. That's less common that you'd be so lucky. But it is very, yeah, it's a pretty easy problem to solve.
All right. Then let's thank Colin again.
Thank you.